Number 10 here deals with the second type of volume problem we're doing in 6.2, where we're building a base and then building similar cross sections up out of that base. Kind of like drawing or building a concrete foundation and then building something up into the z-axis direction from that. So our base here is given to us by x plus y is equal to 1. Now I thought that was interesting. They gave that to us in standard form. So we're going to need to solve that either for x or for y. The first thing I'll go ahead and decide right now, well, not really decide, but decipher. They're telling us now that our cross sections are going to be semicircles here perpendicular to the y-axis. As soon as we read that phrase, guys, perpendicular to the y-axis, that tells us that this is a dy problem. That now tells me that this equation right here should be solved for x in terms of y. So we would end up with x is equal to a negative y plus 1, and I think at this point we can probably start graphing our region here and see where we're at. So x plus y is equal to 1, or x is equal to negative y plus 1. This 1 is now your x-intercept. That's a little bit weird to get used to. So right out here at 1, I don't think I need to go any further than this, guys. So there's our x-intercept, and our slope here is negative 1 as well. Now, it's a weird thing, guys. When you're solved for x in terms of y, your slope is the opposite of what you'd normally think. We would normally say rise over run, but when you're solved for x, your slope is actually run over rise. Left 1 and up 1, and that's going to get us our y-intercept right here of positive 1. So there is the line in standard form looking like that. And they've also told us now the x-axis and the y-axis are going to border this region as well. So there's the x-axis right there, and there's the y-axis, and now I think I can see what we're dealing with here, guys. We've got this shaded region right here. That's going to be the concrete foundation, the base that we're going to build our solid out of. And the shape we're going to create now are semicircles that are running perpendicular to the y-axis. So a segment going from the y-axis over here to the right now to that line, that is going to be the diameter of one of these semicircles right here. So that's why I'm going to go ahead and use the variable d in order to name that. I'd always suggest you guys choose a variable that makes some sense with what it is that we're talking about. Now, really quickly, I told you guys a while ago, once you get the hang of this, it's really not necessary to draw the three-dimensional version of this graph. But for those of you who like the practice here, oh, this is going to be a weird one here. All right, so going about that far, about that far here and about that far here, there's your region right over there. And then we're going to draw this D segment again, perpendicular to the y-axis, which still means parallel to the x-axis. So this is strange, guys. That's clearly a right angle there. When I draw something right over here, still parallel to the x-axis, that is your right angle right there. And now you'll see it in this case here. We're going to be drawing a semicircle coming out of the xy plane up in the z direction. So that's a little weird. All right. What are we doing with this here, guys? Well, the first thing we're going to need to do is come up with the formula here for the area of a semicircle, which is 1/2 the area of a regular circle, which is pi times your radius squared. So our goal now comes to, in terms of expressing r in terms of y, so that we can integrate this with respect to y, as we said just a moment ago. So how are we going to do that? Well, let me go in red right here and say, okay, d, my diameter, is going to be a variable quantity, and it's always going to be measured by the right curve minus the left curve. But again, I've got to keep an eye on the fact that since we are integrating with respect to y, I need everything solved for x. This line here is x equals negative y plus 1, and over here on the left is the line x equals 0. So right minus left is going to give us a diameter here of negative y plus 1 minus 0, and that's just negative y plus 1. So that's our diameter. Unfortunately, we need the radius, and the radius is always half of your diameter. So you could do this a couple of different ways. I think I'm just going to make this 1/2 times the quantity, and I think I'll rewrite that as a 1 minus y just because it's a little bit neater. Now that's important right there, guys. We've expressed r in terms of y. So now I'm ready to go back to this formula right here, but write it slightly differently. Area as a function of y is going to be a 1/2 times a pi, and in the place of the r, I'm going to put in a 1/2 times the quantity of 1 minus y. So all of that in brackets is the radius, and that radius now needs to be squared. And I think it would probably benefit us to simplify that a little bit. You've got two factors in the base, 1/2 and the 1 minus y, they both get squared. So the 1/2 squared is going to make a 1/4, which I'm then going to multiply this 1/2 now to make a 1/8. And I'll multiply that by pi as well, and I think I'll just make that a pi over 8 out in front. And then we've got a 1 minus y quantity squared, and I'm going to leave it like that. Okay, guys, that is our a of y formula, which is always the hard part to come up with here in a problem like this. So let's, can we scroll here? Maybe we can't. All right, let me make a little mark down there. Now I should be able to do that. Okay, and from there, everybody, the rest of this shouldn't be too bad. Volume is going to be the definite integral of that a of y formula. I'll pull the pi over 8 out in front because it's just a constant and leave this as a 1 minus y quantity squared taken with respect to y. And our limits of integration are going to be the lowest and highest values of y in this region, which starts down here when y is 0 and ends right there when y is 1. So the limits aren't going to get a whole lot easier than that, guys. 0 and 1. And now let's see what we can do. I think I'll go ahead and try this one by hand, although you could use your calculator here. We'll keep the pi over 8 out in front. We've got a quantity to the second power. So when we're anti-differentiating, it'll be the same base, 1 minus y, raise the power by 1, that's 3, divide by that new exponent, that'll put a 1/3 out in front, and then divide by the derivative within as long as it's constant. That derivative within is -1, so I'll just put a negative right out there. And all of this gets evaluated now from 0 to 1. So this got a little messy, but it's not too bad. I now have a negative pi over 24 out in front. And then in brackets, let's put the 1 in there. 1 is going in for y, so 1 minus 1 is 0 cubed. That's just 0. Minus, let's put a 0 in there now. 1 minus 0 is 1, cubed is 1. So we end up then with a negative pi over 24 times a -1, which worried me for a minute. I thought my answer might be negative, but it looks like it's going to come out to be a positive pi over 24 cubic units. All right, guys. So that is how we worked out problem number 10 in section 6.2.